Hello everyone, thanks for coming. We're going to do a brief review of our week 2's lecture for ODEs. So first, we introduce a specific kind of first order ODE, which is called the exact equation. So exact equation writes as m dx plus n dy equals to 0. So the condition they should satisfy is that the partial derivative with respect to y for m equals to the partial derivative with respect to x for n. So in this sense, using the Clairaut theorem, actually we can find another function per se such that per se x equals to m and per se y equals to n. So the solution to the exact equation is very simple. Just per se equals to c, because if we take the differential of this equation, we get m dx plus n dy equals to 0. So this is the exact equation, and the key idea is to find, to solve them is to find the per se, such that per se x, y, its two partial derivatives correspond with m and n respectively. So the exact equation actually has something to do with the integrating factor, because finding the integrating factor is to make a non-exact equation become exact. So the general integrating factor method reads as follows. Suppose we have m dx plus n dy equals to 0. Then this is the differential equation, partial differential equation that the integrating factor should satisfy. However, we don't want to solve an even more complicated problem than the original problem, so usually we use an integrating factor that only depends on x. Sometimes we may not be able to find the integrating factor. In that case, we cannot solve that exactly that ODE analytically. This is totally fine. So if the integrating factor mu equals to mu x exists, then it should satisfy this ODE. d mu dx equals to the right hand side my minus nx over n mu. So we need to ensure that the right hand side is only a function of x. It is not a function of y, in order for the integrating factor to exist. With first order ODEs, actually we can model many physical phenomena. So first, we will need some first principle to construct the model, construct the ODE model. For example, the mass action principle to describe how the physical quantities like position, like the concentration of some chemical evolve over time. And then the second step is to analyze the model. Is the model well defined? Does the solution exist, and is the solution unique? Can the model be solved analytically, or is there a numerical solution to the model? Then we compare the simulations or the analytic solution with real data. This is to justify the model, to evaluate the model's performance, and then if we don't know some coefficients in the model, we can determine the coefficients by solving some inverse type problems. As some simple examples, we have those very simple physical models that would utilize the first order linear ODEs. For example, the mixing problem, we have a pound of water, we have inflow, we have outflow. We need to monitor the concentration of chemicals. The population growth model, which characterizes exponential growth. Newton's cooling, that is to put a hot object in room and to model its temperature's evolution. Finally, compound interest. This is compound interest model. This is also similar to the population growth model characterizing exponential growth. Thanks for listening.